Hello students, now we are gonna start our new topic of magnetic effect of current and magnetism. So in this lecture we will study about galvanometer, and I think you have heard about galvanometer before. Can you guess where you heard about it? Yes, in Wheatstone bridge. When we were studying about Wheatstone bridge, we used a galvanometer in it. So what is a galvanometer? So galvanometer is a device which is used to detect current in any circuit, and it can also detect direction of current. So it can detect very small current, even it can measure up to 10 to the power minus 7 ampere. So when we study about galvanometer, one thing we will have to keep in our mind, that galvanometer can detect current in any circuit, it can also detect its direction, but it cannot measure the value of current. So let's start our topic, galvanometer. So students, first we will discuss about what is a galvanometer. So galvanometer is a device which is used to detect the presence of current in any given circuit and to find the direction of current in the circuit. We can classify this galvanometer into major groups. First is moving magnet galvanometer and second is moving coil galvanometer. So first we will discuss about moving magnet galvanometer. So in this type of galvanometer, the coils remains stationary and the magnet is deflected. One of its example is tangent galvanometer. And number second, moving coil galvanometer. So in this type of galvanometer, the magnet remains stationary and the coil is deflected. We can further divide moving coil galvanometer in two parts. Number first is pivoted coil galvanometer or western galvanometer, and number second is suspended coil galvanometer. So first we will discuss about pivoted coil galvanometer. So first we will discuss about construction of pivoted coil galvanometer. So pivoted coil galvanometer consists of two concave permanent magnet where magnetic field is directed towards north direction to south direction, and a rectangular coil with a number of turns made up of fully insulated copper wire is bounded on a metallic frame. This metallic frame is pivoted at both the ends where it is free to rotate between the pivots. Also between pivot and coil, two phosphor bronze springs are connected. The first one is connected to top end of the pivot and the second end of coil is connected to bottom end of pivot. Both springs are connected to other end by a binding screw. A cylindrical soft iron core also placed coaxially inside the coil to increase the strength of magnetic field and to make magnetic field radial, which is directed from north direction to south direction. Also a pointer is connected to top pivot for measuring the angular deflection in the coil, and two terminals of coil are connected to two terminals of galvanometer, later which will be joined to the given circuit. So now we will discuss about its working. We have studied that when a coil is placed in uniform magnetic field and whenever current is allowed to pass through it, a torque acts on coil which tries to rotate that coil. When current is allowed to pass through the coil, direction of current is from A to B in the left arm and direction of current is from C to D in the right arm of coil. And distribution of magnetic field is from north direction to south direction. So we can apply right hand palm rule in this condition, due to which magnetic force will act on the coil and coil will start to rotate, due to which the pointer will also deflect, and here spring will comes into play. This spring is used to restore the coil in its initial position and to also avoid any extra unnecessary deflection which can damage the galvanometer. So it is the construction and working of galvanometer. So students, we have discussed about construction and working of pivoted coil galvanometer. Now we will find what is the relation between deflection of pointer and the current. So to find it, we consider some parameters. Let number of turns in coil is small n, area of coil is capital A, current in circuit is small I, intensity of magnetic field is D, and for the string, modulus of rigidity of spring is equals to C, and angular deflection is phi. So in previous lectures we have discussed that when a coil is placed in magnetic field, then torque acting on coil is torque acting on coil is tau is equals to N I AB, and there also be deflection in that spring. So that spring will try to restore this pointer in its initial position. So a restoring torque will act on spring. So restoring torque on spring, it will be tau is equals to C into phi. But these two torque are equal, so we will put them equal. So we will find N I A B is equals to C phi. So I is equals to C phi upon N A B. So this is the relation between deflection of pointer and the value of current. But here you can see that C, modulus of rigidity, and number of turns, A area, and B are magnetic field, and these all parameters are constant. So I can write C upon N A B is equals to constant. So I can write I proportional to phi. So I have removed this constant and I have got I proportional to phi. So we can write down that the deflection in coil is directly proportional to current passing through the coil. So students, note it down, then we will discuss about suspended coil galvanometer. So after pivoted coil galvanometer, we will discuss about suspended coil galvanometer. So suspended coil galvanometer is more sensitive form of pivoted coil galvanometer. In construction, it is similar to pivoted coil galvanometer. The difference in pivoted coil galvanometer and suspended coil galvanometer is, in pivoted coil galvanometer, 2 springs were used, but in suspended coil galvanometer, 1 mirror will be used at the place of 1 spring, and this mirror will be used to increase the sensitivity of galvanometer. So students, now we will discuss that what is the role of that mirror in suspended coil galvanometer. To understand this, consider we have a mirror, a light source and a scale. So whenever a light beam falls on that mirror, so it will be reflected to its initial path. Say it is our 0. But consider that mirror is deflected by 5 degrees. So whenever this mirror is reflected by 5 degrees, this reflected ray will be deflected by 5 degrees. And we will study this topic in ray optics. So we can see that whenever there is a deflection, there is twice deflection. And the distance between this mirror and scale is B. And this distance is considered to be between 2 to 5 meter. So whenever there will be a slight displacement, there will be a large displacement on this scale. So consider this displacement is x. So now we will apply tan 2 phi in this triangle. So tan 2 phi will be equal to perpendicular upon base, and perpendicular is x and base is d. So tan 2 phi is equals to x upon d. But you can see here, if very less current is passing through that coil, then this deflection will be very less. So this 2 phi will also be very less. So we can write, since 2 phi is very less, then tan 2 phi will be considered as 2 phi. So we will put 2 phi here. So 2 phi will be equal to x upon d, and phi will be equal to x upon 2d. We have also found the relation between current and this deflection. I is proportional to phi, so we can put that value. I is proportional to x upon 2d. But this 2d is constant, so we can remove this constant also, and we can write down I proportional to x. So we can see here that current in the circuit is directly proportional to deflection on the scale. So we can write down that deflection on scale is directly proportional to the current passing through the coil. So students, if this question is asked in your examination, then you will have to write its construction and working. Then you will derive this equation, and after deriving this equation, you will have to write this whole derivation. I think today's topic is clear to you. Note it down, and we will end today's lecture here.